In this video, we are going to try a few questions related to magnetic effects of current, and they are the previous year questions, the P.Y.Qs of the board exams. So they're quite essential, and let's try a few of them. I'll be doing a few of them in this video, and we'll continue doing many more such numericals and conceptual questions in the upcoming videos as well. You can send me your doubts uh, for helping you. So in the first bit, we have two circular coils. They are P and Q, which have a common axis, and they are of equal radius, though they do not seem to be of equal radius in my diagram. But still, they are of equal radius, the radius being equal to r in each case, and they are separated by a distance of 2r between them. And the central point is the point O. Now, in the coil P, it has mentioned that the current flows in the clockwise sense. So this is the coil P and this is the coil Q. And in the coil P, the current flows in the clockwise sense. And then in the coil Q, it flows in the counterclockwise or the anticlockwise sense. Now, the magnitude of the field at the point O is to be determined. Now, as we can see that for the coil P, with the current flowing in the clockwise direction, as I have provided in the application of Biot-Savart's law in the video that is available in the playlist of magnetic effect of current, you would observe that for the current flowing in the clockwise sense, the magnetic lines of force goes into the plane. So the magnetic field due to the coil P, I'll call it as B subscripted with P, that goes along that direction. And then for the counterclockwise sense, it goes out of the plane, and so you'll have the magnetic field due to the coil Q to be directed along that direction, which is away from the plane of the coil. So both these fields act along the same direction, and with them acting along the same direction, the net field is just the addition of both of them, because even in vector addition, if you have two vectors to be directed along the same direction, they will be added directly. And we know the direction, so now we just need to focus on the magnitude. And in fact, the magnitude would be the direct addition of these two, because they are along the same line. And with them being along the same line, we just need to determine their magnitudes and add them up. Well, if you see that the point O is at the midpoint, so you have the distances to be the same, and the general expression for the coil, for the point for the magnetic field along the axis of the coil at a distance x with a radius a, as we know it, is mu naught times of I a squared over a squared plus x squared over 3 over 2. Now here the value of x is equal to r and a is equal to r as well. So all we have to do is mu naught times of I times of r squared over 2r squared raised to the power 3 over 2. And as we know, 3 over 2 is just 1.5. So this is 2 times of root 2. And this one is going to be r cube, and mu naught I, there's an r square over there at the top. Two of those r get cancelled out with that in the denominator, so all you have left is mu naught I over 2 root 2 times of r. Even if it's asked only the magnitude, you know the direction as well. Without knowing the direction, you cannot really determine the magnitude, so that's the way to do it. So this is the required result. Let's switch to the next question. Now, In the next bit, we have two circular coils again, and by the name P and Q as well, and they are arranged in somewhat this form, one at the one perpendicular to the other, where the planes are perpendicular now, and you have to determine the value of the magnetic field at the center of this arrangement. Now, if they are obviously carrying certain amount of current, the current along the coil P is 3 amperes, while that along Q is 4 amperes. Now, what I've shown is that the current flows in that coil P, and if you observe closely from the top view, if you look at it from the top view, it's actually in the clockwise sense. So the magnetic field at that central point is going to go in the downward direction. I'll use another ink for that. It's going to go in the downward direction. So I'll have the field due to P, due to the coil P in the downward direction. And then with Q, you see the arrow uh, on that outside rim or the outer rim, which means if I were to curl my finger, then the field is going along this direction, and that direction being that for BQ, because that rim is towards me, and the other part of the rim is towards the plane of the sheet that you are seeing. So that arrow rim being on my side, that part of the circular loop being on my side, so obviously curling the finger of my right hand, the extension of thumb gives the direction of the magnetic field in this case. And then with these two fields available, we'll get the resultant. Now, the fields are directly proportional to the value of the current because the radius of both those coils are the same. It's been given in the question. I forgot to tell you that the radius of both those coils are the same, and only thing that is varying is the value of current that they carry. So with that value of current along them, uh, and they being perpendicular to one another, you have one of the vectors depending on the value 4 and the other depending on the value 3. Obviously you get a resultant which is exactly equal to, well, by that law you have this to be equal to 5, because these two are perpendicular to one another, not the line in between that I have drawn by mistake. So these two being perpendicular to one another, the magnitude of the resultant is going to be 5 and along that direction. So if we are concerned about the magnitude, then we have the net magnetic field to be equal to mu naught times of I, well, squaring and taking the root of all of them. Instead of I for 4 and 3, you now have 5. The currents are not obviously the vector quantities, but they will definitely uh, give a value to the magnitude. So this is the shortest way that you can approach in order to obtain the magnitude, just by knowing, because the radius are the same. So just by knowing the value of the current on which the magnetic field depends, you have mu naught I times of 2a, a being the radius in this case, which is the same for both of them. You can have any value of radius which is common, which is obviously common for both of them, and you can apply that value. So it's that's not really important. The important thing is that how we approach the problem, and that is how we do it. So this is the magnitude, and you can determine the direction if you wish to obtain uh, how much is it dipping from the plane which is carrying the 4 ampere, from which is carrying the uh, horizontal loop from the horizon it is dipping through an angle alpha. You can determine that, or you can give it in terms of well, this is along the x direction if you take it as I cap, and this is along the j direction if you take it, then it is the negative of the y direction, so minus j hat. So you can put those values over there, and this will be, you'll be through with it. In fact, in terms of I cap and j cap, you will have the value to be equal to uh, B.Q I cap and then B.P along minus j cap. That is how you write it vectorially. But that's not giving the magnitude. So magnitude obviously is equal to, because they are perpendicular to one another, also you'll be getting BQ squared plus BP squared under root directly. So if you are well versed with vectors, then you'll be able to get get the perfect result quite easily. Now comes the third bit in the series, and that has a multiple option where if you are to determine the where you are to determine the variation of the magnetic field with respect to the radial distance. Now the radial distance in this case, well, from the surface of the given coil or given current carrying conductor. So this is the current carrying conductor, a highly magnified cylindrical view of the current carrying conductor, and here the current is distributed uniformly across its cross section, and then you have the axis of that wire or the conductor through which the current flows. Now the current is distributed over the entire area of cross section of the given wire. If we were to consider the radial distance, which is, let's say, in big R, capital R, and then we are trying to determine the variation of the magnetic field within, when we have the R to be less than R, which means any point within, and then we have, at this point we have R to be equal to R, and then finally anywhere outside where R, which is the position of the point taken from the central axis, here R is greater than R. So in that case, this is going to vary like this, where it will go straight, where B is directly proportional to R, in this case within the given within the given wire, and then here at R is equal to R, it carries the maximum value, and then it varies inversely, as we have studied in case of the first application of Biot-Savart's law, that B is inversely proportional to the distance. Actually it's inverse squared, but the expression that finally appears is in the inverse of the distance. So this is just be taken as inverse of the rate of the distance from the axis of the loop, or the, not the loop but the wire. So that's the result that we expect from the variation of the magnetic field with respect to the radial distance from a given straight conducting wire. So that's more or less the question or the rule associated with dealing with these questions related to the current carrying loop, and also in case of straight conductors, how we use the Biot-Savart law. However, the last question that I tried, that is more of the case of Ampere's circuital law, which gives us a detailed result about the variation of the field inside the uh, current carrying wire or conductor. For the outside case, that is the for the small r being greater than R, that is dealt with in Biot-Savart's law. However, the inside of it is the result of Ampere's circuital law. So if you are provided with a question which does not really ask you about the variation of field inside, so you can skip this portion, and you can straight away this portion, which is for the inside of the loop, you can straight away continue from the point on the surface. That is, the variation goes like this. So from the surface at r is equal to r, it varies like this asymptotically along the r axis, value of the magnetic field. The maximum value, of course, is mu naught I over 2 pi capital R for an infinitely straight conductor. So that's it from this video. We'll be dealing with more such problems in the upcoming video. Till then, thank you for watching and keep sending your PYQs. That's all.